presentation is entitled Improved Governor Response at the Dinorwig Power Station. It's going to be presented by two presenters. So first we have Toni Jones. He's the lead control engineer at Dinorwig. He's been there for the last 6 years. And he led the modernization of the control systems. His strengths are in PLC and SCADA systems. He's got a particular emphasis on pump storage. Those of you probably know that Dinorwig is very famous for power plant. Tony's worked in many different industries, from aluminum smelter, steel works, food and drink, medical facilities. He even worked at the Royal Mint. So he went from a job where he could print his own money into hydro. He's a chartered engineer and gained his engineering education at Cardiff University in Wales. The second presenter is going to be Yohe. He's a project engineer, field service, commissioning engineer. He's got many years of experience with hydro governors and controls, including 5 years at Hydro, where he was responsible for testing and commissioning digital governors and plant control systems. He's also an accomplished governor in training. So I'd like to ask you, Toni, to come up and start this off.
Okay, thank you. I'm going to speak about the governor response improvements we made at Dinorwig Power Station. Before we go into the technical details of the governor, I'm sure some of you are familiar with Dinorwig Power Station, but I'd like to give you some background which makes this power station a little bit special, certainly in the UK anyway. It's a pump storage plant in North Wales, and it's about just coming up to 30 years old now. It's got 6 units rated to 320 megawatts. We're operating at a head of about 550 meters, which is about 1,800 feet. It's got 10 gigawatt capacity. And what makes it a little bit special for us in the UK is that it's a very fast responding power station. And an example of that is it can generate about 1,300 megawatts of power in just under 12 seconds. That's from condensed mode, or spin gen as we call it in the UK. And a key feature to meet all those is the governor system. So we identified the need to upgrade the governor a few years ago, and the main driver was obsolete equipment for the control system. We decided not to upgrade the hydraulic system. We felt that was adequate, and so we concentrated on the control system. One of the risks for us really is the commercial risk during commissioning a new governor, and what we decided to do was to commission or build a plant model specific to Dinorwig to try to minimize the downtime during the commissioning period. And an example of that really is we went through about 150 to 200 startups using the model, which was a significant feature for us in the upgrade. It certainly paid for itself in that sense. So what we did then was specify what the requirements were for the new governor for competitive tendering really. And there were some quite specific challenges that needed to be met. And there's two pictures I've got on the top here. The one on the left-hand side shows how dynamic the frequency is in the UK grid. That trend is over an hour, and the extremities, the limits of the frequency is 49.8 to 50.2 hertz. So the frequency collapses and recovers quite a lot daily, and that's not that happens almost daily on the UK grid. So those are the kind of frequency response challenges we had. We had to deliver megawatts quite quickly as well. There were specific requirements with our grid operators, the national grid, to deliver a pre-agreed amount of megawatts in 10 seconds for primary response. We also have wicket gate or guide vane, variable guide vane movement during pumping. The other thing, we were a Rockwell plant as well, and we wanted to maintain and not go to other PLC manufacturers. So the other thing that's not on the slide there is we normally synchronize in about 90 seconds from shutdown, so it's a fairly rapid synchronization from shutdown. So I'll hand you over now to Greg, our American Governor, to describe the technical achievements and how we achieved all of these. Greg, do you want to take over?
First, I want to thank Tony for putting up with me the last couple of years, and I know one day he will appreciate my music when we're listening to his new startups. One thing on this screen too is you can see the penstock that's with the units here. It's very dynamic, and I'll show you some responses when they do a normal megawatt set point change between one unit, unit 1, and we just upgraded another unit to unit 4. And you'll see the responses on that. Some of the effects of the new governor, what we really did was we had to take our standard governor, and then we had to build all the criteria that Dinorwig needed around our standard governor. And also within that, we built a megawatt feed-forward routine. It's very dynamic on how we built that. We added some things in there that, like water start times that are associated with it, and you'll get to see some of that. And also the other thing was the improved frequency response, and we do have a chart at the end that shows some of the differences between the old government and the new government. Again, what we did was we utilized our standard governor, and we built all the specific routines that was Dinorwig's specialties and the criteria around that. For example, we had adapted our code to accommodate the droop setting that was 4% above 50 hertz and a 1% droop setting below 50 hertz. So we actually had 2 different types of droop settings within that governor. The other one of the main challenges, which turned out really well at the very end here, but even though this is a new governor, all the existing HMI screens remain the same for the operators. This way they didn't have to learn a whole new system, and any chances of errors or mistakes or anything else with this was just dramatically reduced. We were sitting in the control room, and phones were ringing from National Grid. They had to control up to what? How many units? Nine units, I believe.
Yeah, 10 minutes.
Yeah, 10. And then so we had to control that. So trying to learn a whole new screen, it just minimized everything for them. Without having to go through. Some of these guys didn't even know they had a new governor until we actually told them. This is an example, it's an actual trend of our megawatt feed forward routine. What we have here in the purple is the set point that was the new set point that needed to be achieved. So it started out at 150 megawatts. The green line represents the actual guide vanes, and the white line represents the net head, and the yellow represents the megawatt feedback. So in this example here, the net head started around 518 meters. The operator entered a new set point. We had a specific ramp rate with the guide vanes. And so after the megawatts were achieved, the net head went down to nearly 507 meters. So that's a difference of about almost 11 meters or 36 feet of head was reduced in this example. The other issue that a lot of governors run into is that there's a lag in the megawatt feedback. In this example here, is about 1.1 seconds behind the actual movement of the gates. So with the algorithm that we built in for the feed forward, we were able to accurately get the megawatt set point in the actual megawatts right on as quick as we can. Now, some of the requirements is that they requested that we have a little overshoot in this, but this overshoot I think was like 4 megawatts, and they requested that because the first time we did this, it went right to 299 megawatts, and so they wanted to have a little overshoot at that point. So that's why the yellow goes over the set point a little bit. Let me go back. Again, this is it for Unit 1. As you can see, the net head in the white and how it dips down and kind of recovers. This is for Unit 4, different part of the penstock. As you can see, the red at the very top here is the megawatts, and the purple here is the gates. As you can see, the megawatts came in and trimmed right on the set point, but look at the net head, how it swung all around. Typically, you would see the megawatt feedback, the megawatt swinging around with that, and then the governor trying to react with that. But the way we built this is that we were able to dampen all that out and have a nice consistent megawatt set point, and then the actuals matching up with the set point, despite what the net head was doing at that point. This chart here is actually a chart that after commissioning was done, we went in. This is about a 30-minute chart. And we're comparing one of the existing governors with the new governor and see how the response was and see what the differences were in this between the two. Again, Unit 1 is going to be in the red, Unit 4 in the blue, and the Unit 6, and the green is the system frequency. So you can see, as Toni was referring to earlier, how dynamic the system is there. So basically, it's a really big island with an islanded grid, and the fluctuations are pretty dramatic. Next slide here, I'm going to be zooming in on that specific sections. Section A shows that you can see in the frequency response, right in this section right here, the red is the new governor, and you can see that when the frequency dipped pretty good right here, you can see our unit responded much better at that point than the existing governor.
At this point, point A there, when we first observed this on plant, we were a little bit concerned that that was overshoot and not droop response. So we went back to the whiteboard and did the droop calculations with the megawatts and the frequency, and taking the water start times into account as well. That is dead on what it should be achieving. So the purple line is underachieving on the existing governors and achieving dead on with the new governor. So we were quite pleased with what we saw there.
Also in section C up top is a part of the program they call it an LF response, or a low frequency response. Within the touchscreen, they have a certain set point that if the frequency drops below that certain set point, then the unit will automatically go full out, go up to its 320 megawatts as fast as it can to achieve the megawatt output to help support the grid at that point. So what happens up here is that we will actually run the gates at 16% per second until we get to our maximum gate opening. And that part up here was 320 megawatts. So you can see both units responded correctly at that point. But the major thing here, as you can see, is that the new governor recovered to its original set point of 320 megawatts within 30 seconds, where the original governor took 2 minutes to recover at that point. So now we're sitting at 320 megawatts. So that was our response. Within that change right there, we could go from 150 megawatts up to 320, which is a gain of about 170 megawatts. And we can do that in less than 10 seconds. So it's quite a amount of load to be picked up in a short period of time. And then the last section, you can see is a really major part there, is in section F. right here. As you can see, the response then of the frequency, as it dips, you can see the response of the new governor going up pretty rapidly, and then recovering and then going up again. But the old governor just really tapered out and didn't respond as well as it should. And that's where the big differences we found with installing the new governor at that point. And this is pretty much it. Yep. The other thing, when we instituted, just to get back, we did the Control Logic platform. We actually made the governor a remote I/O rack over the ControlNet platform, communications at Al Bradley's. And we were able to update all the I/O that are associated with that rack in 5 milliseconds worth of I/O. So we didn't need another processor in that rack, which made it really nice and streamlined at that point too. And the last thing for the upgrade is that they had this huge speed monitoring system. It took almost a whole cabinet just to tell them, where the speed is of the unit. Basically, we ripped all that out and put one digital output card in to replace all that. Now we can interface directly with the processor instead of having all these different communications out to the existing units.
Yeah, we actually still have time for a few questions as well on this.
You said you use ControlNet for the communication platform. Did you get the same update speed Ethernet?
The issue with Ethernet is not very deterministic. So you have an open platform, basically it spans all that information out. And so I would probably recommend not going with Ethernet at that point. What we did is with ControlNet, it's very deterministic and very time-stamped. And he set the ControlNet up at 5 milliseconds. 5 millisecond updates at that point, and it was just consistent all the time. So, and then our program scan at that point was 15 milliseconds. Yeah, 15 millisecond updates and all the government routine.
The initial condition of the hydraulic circuit has an importance regarding the dynamic performance of the turbine, or that is to say, you have to wait for the dumping chimney to stabilize, or whatever the hydraulic condition, the performance are the same.
Yeah, what it did was in the megawatt feed forward, I called it. In the megawatt feed forward routine, what we did was we actually built in a water start time that's variable for each one of the units. So I was able to incorporate that with the PID. That, as you saw between Unit 1 and Unit 4, there's a huge difference between the two. And so with the built-in water start time calculations that we did, I was able to manipulate the values and get the same results from Unit 1 to Unit 4. So, did I answer your question? Okay. Okay. It's hard for me to hear, so actually we're both hard of hearing, so it was a real treat working together in the plant. we got a lot done because we didn't talk. He just listened to my music. That's all. So.
Maybe that's the reason you're hard to hear.
Yes, are we? Yeah.
Yeah, just an associated question to the improved governor response. Was there any considerations to the turbine and generator in this situation?
I can repeat the question.
Okay.
I just want to know if there's any considerations for the turbine and generator in the upgrade.
No, we concentrated on the governor on this now. It was just looking at the governor.
To go along with that question, we kept all the existing controls for the hydraulics. So you had the original converter governor there and everything else. We just interfaced all the signals to the existing equipment. So that was another nice plus in this whole situation too. So.